Good morning. So my name is Martin Manuel, and I work at the University of Edinburgh in the lab of Professor Peter Krein. Our lab is part of the Simon Initiative for the Developing Brain. And today I'm going to show you some of the behavioral and cognitive experiments that we've done on the CHAMP1 knockout rat. So first of all, why did we make the rat? Because there was already knockout mice, so why did we decide to make the rat? So rats are not just like bigger mice. They're closer physiologically to humans. They also have like a rich behavioral profile, which allows for more sophisticated studies of learning, memory, and they also have like complex social interactions. They're also much bigger than mice, and they've got larger brains, which can be a major advantage for instance, electrophysiology experiment or functional imaging. They're also easier to handle, like some people have them as pets, for instance. And that can also be an advantage because when it comes to doing the behavior experiment, then if you've handled them a lot before, they're not as stressed. And also now with modern genome editing techniques, it makes the generation of transgenic rats easier. So our CHAMP1 knockout rat was generated by deleting the whole coding sequence of CHAMP1, which is located in exon 2 of the gene. And so we've got heterozygote knockouts, which still have one normal copy of the gene. And we also have homozygotes, which have no remaining copies. So in our rat, the homozygotes are viable. We did many experiments to validate the rat, but here I'm just going to show you experiments that looked at protein levels. Don't know if you can see here. So here I'm showing you two sections through the brain of wild type and CHAMP1 knockout embryo. So it's an homozygote knockout embryo. And these have been stained with an antibody against CHAMP1, which was provided to us by Kozo Tanaka. So the green fluorescence you can see on the wild type side, that shows where the CHAMP1 protein is expressed. On the CHAMP1 knockout section, don't know if you see very clearly here, but there's no green fluorescence, so we don't detect any CHAMP1 protein. On this side here, I'm showing you also looking at the protein, but this time by Western blotting. And here we have compared CHAMP1 protein levels in the brain of wild type, heterozygote knockout, and homozygote knockouts at different stages of development from embryonic day 17 to postnatal day 23. And so the first thing you can see is that, again, we don't see any CHAMP1 protein in the homozygote, which is good. But what's interesting is that when we look at the levels of CHAMP1 in the heterozygotes relative to the wild type, early on, like in the embryo, so that's shown in the graph here. Early on in the embryo, we find that the levels of the CHAMP1 protein in the heterozygotes are about 50% of that in the wild type, which is what we would expect. But then later on, it seems that the difference becomes like smaller. So it looks like there's some kind of compensation happening. So as I said, we've got CHAMP1 heterozygotes. So these ones still have one copy of the gene. So these are the model for haploinsufficiency. And these heterozygotes, like, they look normal. We can breed them, like, they look like pretty much normal. The homozygotes, so they're viable, but we don't get as many as we expect. So in litters, we get only 10% of homozygotes when we would expect to have 25%. And also they have like a severe failure to thrive phenotype. So on this graph, you have the growth curve of wild type homozygotes and heterozygote pups. So it's from day 3 after birth. And in red is the homozygote, and you can see that they are putting on weight a lot slower than the wild type and heterozygotes. And actually, for a very long time, we were not able to age them past weaning age. So weaning age in rat is around like 21 days after birth, because a lot of them would just, they're so small and they don't grow very well, and a lot of them would just die. So we kind of stopped trying to age them because we get in trouble otherwise. So now we're following a procedure to support their development, and that involves like reducing the litter so that they have better access to their mother's milk. We also delay the weaning age so they stay longer with the mother, and we provide them like with a dietary supplement jelly to kind of help them put on weight. And following that procedure, we've been able to get them to adults and perform behavior experiments. So first of all, we performed some neurodevelopmental reflex tests on the pups, like quite early on in development. And here I'm just showing you one of the tests we performed, which is the writing reflex test. So that's done from day 3 after birth. And so in that test, the pups are placed on their back, and they're given 15 seconds to turn themselves back on the right position. And we repeat that 3 times every day. And so what we find is that the wild types and heterozygote pups, usually they succeed in that task like by day 5 or 6. Most of them can do that. However, the homozygotes, there's a delay, and it takes them a few more days to manage. So usually it's not until like day 9, 8 or 9 that they manage to all 3 times succeed writing themselves in 15 seconds. So that means that they display a delay in the acquisition of those neurodevelopmental reflexes. So now I'm going to show you a few of the behavior experiments we've performed on the adults. So this work is still ongoing. So for some of these experiments, we have quite low numbers still. But yeah. So the first test I'm showing you is the marble interaction test. So in this test, the test rat is placed in an arena with marbles. And those marbles are like novel to them, like they haven't seen them before, like they're a novel object. And we leave them for 20 minutes, and we monitor, like we record how much time they spend manipulating the marbles with their paws. So hopefully that works. So you've got the wild type on the left, and the homozygote, it's an homozygote knockout, on the right. So you can see the wild type starts like manipulating the marbles, like rolling them with their paws. And on the other side, you can see the homozygote knockout doesn't seem that interested in the marbles. He's more interested in trying to get out of the arena. So on this graph, you have the result of our test. So this was performed on all 3 genotypes, wild type, heterozygote, and homozygote. So the wild types are the black bars, orange heterozygote, and the beige color is the homozygote. And we did that in males and females. The numbers are still a bit low. So the graph shows the time they spent manipulating the marbles. And what it shows is that we couldn't see any difference between the heads and the wild types, but the homozygote spent a significantly lower amount of time manipulating the marbles. So CHAMP1 homozygote knockout rats display reduced novel object interaction. In this other task, the test rat is placed in an arena for 15 minutes with 2 of the same objects. So here those blue squares. And then they left for 15 minutes to explore these objects, and then they're taken out. And after either 5 minutes or 24 hours, they're put back in the arena with 1 of the same object and a novel object. And because rats are very curious, normally they would be more drawn to the novel object. So here we're testing their short-term memory of the blue square or their long-term memory of the blue square. So if we look at the short-term memory test, so first of all, this graph here shows the time, both genotypes that was done on wild type and homozygotes. I only have the data for males. So first of all, this graph shows that, like we saw with the marble test, the homozygotes tend to spend less time exploring the objects. And then the discrimination index shows whether they were more interested in exploring the novel object or the familiar object. And if the discrimination index is positive, as on this graph, then it means they spent more time exploring the novel object. So as you can see, we didn't see any difference in the discrimination index in the wild type and homozygotes. So they both were more interested in the novel object. And we get the same result with the long-term memory test. And it's even more obvious on that, on that graph that the homozygotes spent less time exploring the object, but they showed the same level of interest for the novel object as the wild types. So this shows that the CHAMP1 homozygous knockout rat display normal object recognition memory. So in this next test, the social exploration test, so the test rat is put in an arena on its own for 5 minutes, and then a stimulus rat, so an unfamiliar rat, is added. And we record how much time the test rat spends exploring the unfamiliar rat. And again, this was done on all 3 genotypes for both genders. And we didn't see any difference in the time the different genotypes spent exploring the novel rat. So the CHAMP1 knockout rats, heterozygotes and homozygotes, display a normal level of social exploration of an unfamiliar rat. In the tape test, a sticky tape is put on the back of the rat, covering the nape of the neck. And at the top, you have the wild type. And you see that the wild type rat reacts to having this sticky tape by shaking itself like, we call that wet dog shakes, like shaking itself like a wet dog. And I can maybe put it back. And the homozygote rat at the bottom, you can see that it doesn't look like that bothered by having the tape, like it doesn't seem to be, he seems more interested in trying to get out of the chamber rather than, he doesn't seem to notice he has the tape. So this was only done in males, wild type and homozygote so far. And basically it shows that in the homozygotes were performing a lot less of the wet dog shakes within the 5 minutes compared to wild types, which shows that they display a reduced tactile reactivity. And finally, in this last task that I'm showing you, that's the pre-capture test. And in this test, the rat is put in an arena with a live cricket and is given 2 minutes to catch the cricket and eat the cricket. And this is repeated 4 times per day over 5 days. So I'll show you the wild type first. So the wild type is put in the arena, he spots the cricket, goes for it, catches it, and eats it like quite quickly. The homozygote, I had to crop the video quite a lot because he was not noticing the cricket for a very long time. So when eventually he notices the cricket, but doesn't seem in too much of a hurry to catch it. and then when he finally goes for it, it's not that good at it. So we think he caught it, but actually no. The cricket is still here. And I stopped the video because it was going too long. So the result of this task, so this was done on all 3 genotypes, but I only have the data for males here. So this is showing the time it took to catch the cricket from the start in the 2 minutes. And it's showing the different days, day 1 to day 5. And so basically what we find here is that there's no difference between the wild types and heterozygotes. And they get a little bit better after the first day at catching the cricket, so they take a bit less time. But the homozygotes take significantly more time to catch the cricket on all the days. So the CHAMP1 homozygous knockout rat display reduced hunting skills. So this work is still ongoing. We need to, we have more tasks to perform, and we need to increase our numbers. But so far, what it showed is that we did not find any behavioral or cognitive alteration in the heterozygote knockouts, which are the model for haploinsufficiency. However, we have a clear behavioral phenotype in the homozygotes. So I already optimized the delivery of a gene therapy vector to re-express CHAMP1. And now that we have a clear phenotype in the homozygote, I'm going to be able to test whether re-expressing CHAMP1 can rescue some of these phenotypes. And finally, I just want to, and we are also making a new rat model of CHAMP1 loss of function variants now. We chose to model the nonsense mutation arginine 497, which is both pathogenic and recurrent among patients. And that should basically help us test as well the dominant negative theory. And to finish, I just wanted to mention that we performed a single-cell RNA-seq analysis on a piece of cortex from wild-type and CHAMP1 homozygotes rats at postnatal day 7. And this identified many differentially regulated genes in excitatory neurons, astrocytes, and oligodendrocytes. And if anyone is interested in looking at the data, we are happy to share the data, so just email me. Thank you very much for listening.
Thank you very much. Are there any questions? You should come closer, otherwise I will. Kidding.
Hey, really, really great talk. Really cool data. It's super interesting that the homozygous mouse model, as reported by Koza's group, was neonatal lethal, as opposed to your guys' rat model. So I was hoping you could speak to that a little bit. But I'm also just curious, do you guys see any like higher incidence of like tumors in the homozygous knockout, or any other?
Not that I know of,
no.
no.
Issues?
I mean,
okay. Interesting.
No, okay. I don't think so.
Okay.
In relation to why I think the rat is viable as opposed to the mouse. So first of all, I think there are some other group that have a mouse knockout that is actually viable. Okay. So there are several, I think I've heard that in talks before. But also, all rats are in an outbred background, so, and mice are quite often on inbred background, so that might make a difference as well, I think.
Sure, cool, good point, yeah.
Yeah, that's very interesting. I wondered, for other genetic defects like ERCC1 mutations that are involved in transcription and repair, damage responses, predisposition to aging and neurodegeneration, caloric restriction seems to improve outcomes a lot. And this has been done all the way up into children, patients, Jan Hoymakers and colleagues. I'm wondering if you're considering caloric restriction for your homozygous mice to see how that might impact some of these nice behavioral models you have.
Right, so for the moment, my focus has been more on getting them to put on weight so that they wouldn't die. So no, I haven't restricted their diet at the moment. We could do it because, as you could see on the videos, once we support their development with like dietary supplements, and once they reach adults, they're not that much smaller anymore than the wild type. So maybe once they pass the danger zone, maybe we could try.
Well, these children with the RCC1 mutations are very, very thin and very small. And the doctors actually tried to prosecute Jan Hoymakers for trying to restrict their diet. But it turned out they put on more weight, and they went from being unable to walk to being able to walk and ride a bicycle and speak. When they were, basically you're reducing inflammation and reducing a fight between transcription and damage responses. So you might look at his papers and see if there's an analogous way forward, because I mean, it's paradoxical. You would think less food would be worse, right? But turns out not to be the case. Obviously, you have to give them enough vitamins and nutrients, but to reduce that inflammation would be I guess, the test, I suppose.
Well, we could try. We could try.
Very nice talk. I have just two very short questions. The first one is, looking at the data, it looks like translating the data to human beings, it looks like only those with dominant negative effect mutation should develop something more than those one with haploinsufficiency, because we are using the full knockout, not the homozygous. All the heterozygous were roughly normal, behave as a normal.
Yes. Yes.
Yeah, and the second, of course, it makes sense to take in consideration males and females, but are you expecting something different in your model, because the genes are not related to X and Y?
I don't expect anything. It's just the way the experiments are done by the behavior team. They always separate males and females, and that's because they do the analysis of a lot of other models, and some of them show clear differences between males and females. So that's the way they do it. They separate it from the start, so that we don't know until we've checked, I suppose. So.
Thank you. Yeah, to follow up on that question, do you feel that the homozygous model is a good model to represent the clinical condition, which is heterozygous?
I mean, we didn't. So when we first made the rat, there was not this talk about dominant negative. So we made it thinking that the heterozygotes would be the model. So I don't really know that the homozygote knockout is really a model. It's probably, if the dominant negative ID is true, I guess they're probably a closer model to the loss of function variants than the heterozygote. But I don't know whether they, I don't know, you could call them a model, which is why now we're making another one, which would have a loss of function mutation.
And I suppose it's useful that you got the mouse and the rat, you know, one of which is homo and one of which is hetero.
Mm-hmm.
Yes, hi. I had questions, but if you don't mind, I would like to comment on last question from you. So actually, mouse rat and mouse and rodent model for human diseases. It's not easy. They don't repeat human features, and quite common when we get mouse model, you don't have any phenotype. And for my other project, we were doing type with it. We thought it's going to be type 1 diabetes model, but we got like complete neurodevelopmental mouse model. Like we knock out one gene. And so basically, when we're working with animal models, we expected to have similarities with human diseases, but it's not happening quite often. So it's kind of, we're trying our best, yeah. And to your for your rat model, so if I'm not mistaken, it's like deletion of big chunks. So it's deletion of whole gene, right? Like
Yes, the whole coding sequence, not the whole gene.
right.
Coding sequence.
So when you get your single mutation, you might get different, like more severe phenotype, or like
Yes, so that we don't know. We don't know. Yeah.
And my last question, so for gene therapy, what are you planning to use as vehicle? Like how are you planning to deliver
so we already have a vector, and that's expressing, that's basically re-expressing CHAMP1. So we tried, when we tested it with like a very strong promoter, and then the endogenous promoter, and they both worked nicely in wild type, so we decided to stick with the endogenous promoter. So it's like the coding sequence of CHAMP1 with them.
Thank you so much.
Yeah.
Good job.
Other questions? Okay, I have a silly one. How much does a CHAMP1 rat cost?
I don't know, because I didn't pay for it myself.
But is it cheap or not?
I don't really know.
No?
I couldn't say. I mean, you have to ask Professor Peter Kine, because I don't really know. To make the rat, yeah.
Yeah, this is what I was asking, because one of us who are not scientists do not understand how costly it is to produce this kind of models, living models.
I mean, I'm sure we do it in-house, so we have people to do it. Yeah.
You do in-house, so you save money. That's great.
Hi.
Thank you very much for your presentation. Just a question or a comparison from a clinical point of view. Looking at clinics, it seems that CHAMP1 is a dosage-sensitive gene. However, clinical features associated with the deletion, as in your animal model, and associated with the truncating variants seem to be quite different to each other. So to me, it's very important to have a confirmation that CHAMP1 is important. It is a dosage-sensitive gene. But looking at the typical CHAMP1 disease, it is caused by truncating variants. I'm afraid that this model cannot suggest crucial correlations. This is just my idea from a clinical point of view.
Yeah, so that's why we're making the other one, so that we can compare, basically.
Yeah. So we look at your future experiments.
Are we done? Okay. Sorry? You might have a question? Kozo, okay.
Okay. Hi. Hi. Can you hear me? So that I was impressed. So that with the data that you could, make the homozygous rat to survive by feeding them with jelly or something. So does that mean this growth retardation is caused by the defect in the behavior of drinking milk or something like that?
Sorry, I didn't catch the last sentence. During what?
Okay, yeah. So what is the reason for the this failure to thrive?
So I'm not completely sure. So when they are born at P0, I can't really see a difference in the size, but it very quickly, like within 1 or 2 days, they look smaller already. They can't, and because they're smaller, and the difference with their siblings becomes like bigger, they can't compete for the mom's milk. So very soon, if it's a big litter, for instance, they get worse and worse. But I've also had, I also think that some of them may have like, I don't know, digestion problems maybe, or I don't know, because I've had like, some that died, and then when we did an autopsy, they had absolutely no food in their intestine or stomach. So I don't really know what is causing it, but
okay.
yeah.
So after weaning, they catched up with the wild type rat.
So after weaning, I still feed them the jelly for some time until I'm sure that, until I see them with my own eyes eating the dry pellets that we feed the rat. When I see they can eat that, then I stop. And then we found that after that, they're still a bit smaller like that the wild types, but the difference becomes a lot less. Yeah, so they seem to catch up, yes. Once they're weaned, there seems to be like a critical period where...
I see.
Yeah.
Okay. Yeah. So are they fertile?
Are they? Oh, I don't know, because I don't know. I haven't tried that. I mean, I could try with the males. I don't know that the vet would allow us to try with the homozygotes. I don't know. So yeah, I haven't tried to breed them.
I'm just curious because CHAMP1 has expression in testis or other kind, so that may have some other function in other organs. Okay,
yes.
Yeah, that's great. Yeah, thank you very much.
You're welcome.